Good evening everyone. This is a demonstrative video of half subtractor. So half subtractor in nature is very similar to half adder. It has two inputs, input 1 and input 2. And remember, in half adder the sequence is not that important because the addition does not specifies that 5 plus 3 and 3 plus 5 are different. But in subtraction, 5 minus 3 and 3 minus 5 is definitely different. For that reason, remember the yellow LED is our first input and green LED is our second input. Okay, now this is the red LED, which is the difference, or the you can say the result of our subtraction, and this is a borrow LED. uh, the two outputs are there, two input, this is input 1, input 2, and these two are output of our half adder. This is the difference and this is the borrow. Every LED's ground terminal is connected via a current limiting resistor for each LED to the ground terminal of my power supply, and this current limiting resistor is 330 ohms to protect my to protect my LED from overcurrent. Okay, so yeah, this yellow wire, so there are two yellow wires. These two yellow wires have the signal of the input signal 1, and these two green wires are connected to the input signal 2. Okay, so there are total 4 NAND gates in this first IC 7400 and 4 NAND gates in this second IC 7400. I am using 4 NAND gates of the first IC and the first NAND gate of the second IC. Okay, so first NAND gate of the first IC is operating on the basis of these two input signals and giving the output signal at pin number 3, and that pin number 3 is connected to pin number 4 via a very small black wire, this small black wire, and another small wire which is connected to pin number 3 and pin number uh, 10, I guess. Yeah, pin number 10. So yeah, this pin number 4 is the first input of the second NAND gate, and this pin number 10 is the first input of our third NAND gate. So that output is getting spreaded between, or getting connected between, the two inputs of our different NAND gates in the same IC. And the NAND gate needs two input. The first input is connected to the pin number 3, and second input of this particular NAND gate, this second NAND gate of the IC, is connected between this black wire which is connected to pin number 3 and this yellow wire which is connected to pin number 1, or we can say that it is connected to signal 1. This is our signal 1. So it is doing the NAND operation between signal 1 and the output of from the pin number 3. Same here, this green wire is connected to signal 2, and here this third NAND gate of our, let me turn off the power first because this is metal. So yeah, so this is the third NAND gate of our IC, and this third NAND gate is doing the NAND operation between this pin number 3's output and this signal 2. Okay, so and the output is getting provided in pin number 8, the output of this particular NAND gate. So that pin number 8 connected is connected with two terminals, pin number 13 here, sorry, pin number, yeah, pin number 13 here, and pin number 1 of this, pin number 1 of our second IC. Okay, I will tell the reason later. So here in the pin number 13, it is connected to pin number 8, which is the output of our third NAND gate, and this is the last or fourth NAND gate of our IC. And this fourth NAND gate is doing the operation between these two blue wires. These two blue wires are the input terminals for this particular NAND gate. Okay, this blue wire is getting the signal from this second NAND gate of the IC, and this blue wire is getting the signal from the third NAND gate of our IC. Remember that this is our output of the third NAND gate, this blue wire, and this blue wire is the output of our second NAND gate. And in the fourth NAND gate, we are doing the NAND operation in between these two output lines and getting the result directly in the red LED, which is connected to the ground via a CLR. Okay, so ultimately this configuration you will see in most of the circuit, because this is ultimately replicating a XOR gate, nothing extra, just a simple XOR gate and nothing extra. Okay, so this circuit is very common in most of the circuits, and this particular IC I am using just for a simple one NAND gate, and that NAND gate is acting as a NOT gate because I have shorted pin number 1 and pin number 2, the both input terminals, with this white wire, because I need a NOT gate here. To how to get a NOT gate from a NAND gate? The answer is simple. We just need to short the both input terminals. So we shorted the both input terminals to act as a NOT gate, and this is the signal coming from the pin number 8. Okay, so this pin number 8 signals getting inverted here, and the output is connected via this black wire to this blue LED, which is again grounded with the current limiting resistor. This red wire is powering this second IC. This is the VCC and this is the ground. Again this black wire is for powering the first IC. This is the ground, and this red wire is the VCC for the first IC. So yeah, all is done, everything is done, and let's see the input outputs of the circuit. First, power it on. I have powered it on. So this SPDT, single pole dual through switches, are at in ground state, I mean at 0 signal. So the both signals are 0 right now. So if we do the subtraction of 0 and 0 in binary, the the difference is 0 and the borrow is of course 0, because 0 minus 0 is everything 0. If we do 1 minus 0, so 1 minus 0 is 1, difference is 1, there is nothing extra borrow. Okay, so if we do 0, if we do 1 minus 1 first, okay, 1 minus 1, so this is 1, first one, and this is the second one. 1 minus 1 is 0 in difference, and also in the borrow is 0. The last combination is 0 minus 1, which is tricky. So first input should be 0 and second input should be 1. So 0 minus 1 in binary gives difference as 0, and also carry as borrow as 0. So it's how the binary subtraction works, and there is nothing to explain more. So these are the so this is the total 4 conditions of binary subtraction, and this is a half subtractor, not a full subtractor. In the case of full subtractor, there will be 3 input. There will be a carry in from the previous stage. So yeah, in half subtractor there is 2 input, input 1, input 2, and 2 output, difference and borrow. This is nothing but a very similar circuit to a half adder, and yeah, nothing special here, and it's all done. So one thing I forgot to mention in the half subtractor circuit is that why we connect. So in this particular scenario, you can see that the this particular white wire is connected to the pin number 8, which is not our final output. Final output is pin number 11, 13, 12 here. The final output is in our pin number 11 here. So this pin number 11 is our final output, and we are inverting the signal not from the final output, from a particular pin number 8, and I will tell the reason why. So if you look at the truth table of a half subtractor, you will see that the difference the borrow is most of the time 0, 0, 0 and 0. Only at a particular situation the borrow is 1, when the first input is 0 and second input is 1. Okay, 0 minus 1 needs a borrow, so for that borrow the borrow is 1 here, and every other situation is 0. So to mimic this truth table's behavior of input output, we only can achieve this by this particular boolean expression, where the borrow out also, by the way, this borrow is called borrow out because when we do the full subtractor there also a borrow in, for that reason we call it borrow out. So the to get this particular truth table's behavior, we will calculate basically the boolean expression for the borrow out is looks like this: a naught dot b. So if a is 0, a naught is 1, and if b is 0, then 1 dot 0 is 0. Okay, I mean, if suppose in the first truth table there is 0 0 both a and b, so if b is 0, no matter a is what, the this expression will give 0 because it is a AND operation. So if b is 0, then it will be 0. So these two conditions are eliminated where b is 0. These two are left where b is 1. So let's take the last one where a and b both are 1. So when a and b both are 1, a bar or a complement or a dash, whatever you call it, it will change from 0, it will change from 1 to 0, and 0 dot something will definitely be 0. So this particular condition will also give a borrow 0 as per this particular boolean expression, and remaining row of the truth table is this particular row where a is 0, b is 1, and that borrow should be 1. So let's see, when a is 0, this a complement inverts that 0 into 1, and b is already 1 here, so b is 1, and 1 dot 1 will give definitely the borrow out as 1. So to get this truth table's nature for the borrow, we need the boolean expression for the borrow out like this, and we can achieve this by, we can only achieve this one second. So see, the this is the eighth pin of the IC, and we need to do a NOT operation from this particular pin here. And why from this particular pin? To get a bar b, we evaluate the NAND gate circuit, and we see that if we do the NOT operation from this particular pin, the De Morgan's theorem will help us to get a bar b, and this is a part of the theory, boolean expression and boolean arithmetic. So you have to do the theory first before the practical. So yeah, that's all. So this is the circuit schematic of a full subtractor using NAND gates. There are total 9 NAND gates. These are the 4 NAND gates of the IC1. These are the 4 NAND gates of the IC2, and this particular NAND gate is from IC3. The all of the ICs are IC7400, which is 2 input quad NAND gate. So each IC has 4 NAND gates in total. So 4 one IC, another 4 another IC, and for this one I need to use extra IC. So this is the total circuit schematic. The full subtractor has 3 inputs. So this is the input 1, the first input of our full subtractor. This is input 2, also called B. I named it B. This is the second input of our full subtractor. This is the B in, which is the borrow in. It is the borrow from the previous stage, and this is the third and the last input of our full subtractor. These are the two outputs of our full subtractor. This is called D or for difference, and this is called BO, B suffix O, for borrow out. This is the total schematic, and if you are familiar with the theoretical part of the full subtractor, you already know that this is the these 4 NAND gates are behaving as a XOR gate, which is uh, which is actually doing the operation of XOR between A and B. A XOR B, and that output is feeding in another XOR gate, and this 4 NAND gate is a XOR gate, and this XOR gate is operating with the output of A XOR B and the B in. Ultimately, in the difference, we get A XOR B XOR B in. So this is how the difference is getting calculated in full subtractor. And in the borrow, we do the NAND operation of 8th pin from the both IC truth table. You can see that the truth table is it is built such a way, or it has such a relationship between the 3 input pins and 2 output pins, that we can evaluate that the difference is nothing but A XOR B in, which is ultimately getting here A and B get the XOR operation, and the output gets the another XOR operation with the third input, and getting the output is A XOR B in. Clear? But why we take borrow out like that from 8th pin of the second IC and 8th pin of the first IC, and do the NAND operation of them? So if we look at the truth table and evaluate the boolean expression, for the borrow out, we will evaluate that the borrow out has a expression like this, where a bar b plus, we can call it A bar and B, or A bar and B in, or B and B in. So dots are called AND in logical operation, and pluses are called OR in logical operation. So yeah, so borrow out's boolean expression looks like this, and we can evaluate this expression from Carnot map, and if I am not wrong, we can evaluate this from Carnot map and sum of product feature of the I mean the method of sum of product, SOP. So this is again part of the theory, so we have to clear the theory first before the practical. So this is the truth table for the full subtractor, and this is the boolean expression for the borrow out. But it looks like that this expression is not getting matched here, because we can see there are the odd operations between three inputs, so we can assume that there should be a OR gate which has three inputs, and in each input there should be these values, and the OR gate will do the operation, give us the borrow out. But instead we see there is a NAND gate which has only two inputs from 8th pin of the second IC and 8th pin of the first IC. So if you do the simple calculation with taking the different values for A, B and B in, we will see that the borrow out is giving the same result as this boolean expression. So yeah, this is the expression for the borrow out, and this expression can be restructured by a single NAND gate which takes input from the 8th pin of the both ICs, both XOR gates, you can say like that. This is a XOR, this is also a XOR, and these two XORs are helping to get us the A XOR B in here in the difference, and this is the part of the schematic, and this is the experimental value. So zeros, this is the signal in the TTL logic or the CMOS logic. 5 volts or near 5 volt considered as logic 1 or logic high, and 0 volt is considered as logic 0. So I take all the measurements in the practical, and there is the log sheet of that. And let's show the circuit here. So here the circuit looks like this, and there is nothing special into it. It is as per the schematic I showed you earlier. So let's put all the input first 0. The left side of the SPDT, this is the slider switch, also known as SPDT switches. The left side is connected to black wire to the ground, and right sides are connected to the red wire to the VCC or 5 volt supply. So all the switches are on the left side, so all the input should be 0. This is the first input, this is the second input, and this is the borrow in. So we can say that this is A, this is B, this is borrow in, this is the difference here, and this is the borrow out. Let's turn on the circuit. So circuit has been turned on, all the inputs are 0. So when all the inputs are 0, as per the truth table, the difference and the borrow both should be 0. Okay, as you see in the truth table, there is 0 0 0 and 5 zeros in the first row, so it's like that. So when we do the high signal only in the borrow in part, the difference and borrow out should also be high, and I will attach the truth table when editing the video. So this is the second row of our truth table. In the third row we have B1 and A and borrow in both 0. So this is our B is turned on, and A and borrow in both 0, and in this particular scenario the difference and borrow out both should be 1, and both are 1. Okay, third row also cleared. Let me turn it off. Okay, at the fourth row we give B high and borrow in high, I mean 1. So B is high and borrow in is high. In that particular situation difference should be 0, which is 0, and borrow out should be 1, which is 1. So fourth row also clear. Let's turn off again. There is a loose connection problem and nothing serious here. Due to the loose connection it's fluctuating. Okay, so at the fifth row the A is 1 and everything else is 0. So when A is 1 and everything else, I mean every other inputs are 0, the difference should be 1 and borrow should be 0. Simple. Borrow out, this is borrow out, this is borrow in. Okay, at the sixth row we give A high and also the borrow in high. So when we give A high and the borrow in high, we get difference 0 and the borrow 0. So at the seventh row we give A and B both high, but we turn off the borrow in. So when A and B both are high, the difference again should be 0 and borrow should be 0, because 1 minus 1 is 0 and borrow in is 0. So 0 minus 0 again 0. So difference is 0, borrow out is also 0. At the last row of our truth table we give all the inputs, I mean A, B and borrow in 1 or high. So if we subtract 1 from 1 we will get 0, and if we subtract 1 from that result is 0. So 0 minus 1 is 1. It's a boolean, or you can say binary subtraction. So 0 minus 1 is 1 in this particular scenario, and the borrow out should be again 1. So all the truth tables values are rectified in this particular demonstrative circuit of full subtractor. And again, I am not gonna explain the wiring. The pin diagram is already mentioned in the schematic, and I have tried my best to match the color coding, because this green one is the second input, this green one is the second input signal, yellow wire is the first input signal, this yellow wire is the first input signal, but this green wire is not the second input signal, this green one is not the second input signal, same as these two yellow wires, because I have the color limitation. I have total 5 colors in my hand, I mean in my neck technically. So this is the wires. uh, so these are the wires. I have blue, yellow, green, and red, black. So 5 colors are there, not so many. And again, I have the same LEDs. I mean, black LED does not exist, so for that reason, I have the white LED, and it's funny, whatever. So yeah, that's the total circuit. And see you in the next practical, I guess.